Hi and welcome everybody to the 10th lecture of Digital Communication Systems. In today's lecture, we will talk about a new topic called correlative level coding or dual binary coding for doubling the transmission capacity of communication systems. Basically, we will understand what's correlative level coding, why do we use it, and how it works, and also its merits and demerits and how to address its demerits or drawbacks. Correlative level coding is basically a method to add or introduce artificial inter-symbol interference in the transmitted bits in a controlled manner. By adding this inter-symbol interference, it would be possible to achieve a signaling rate of 2 W symbols per second in a channel of bandwidth equal to W. This means that you double the transmission capacity of your system. And this is very significant, very important actually. The basic idea of dual binary signaling is to come up with a new signaling scheme so that you add your symbols and bits in such a way that they become on top of each other. And at the receiver, you can handle and resolve this interference and get your data back. Dual means, what dual mean here? Means doubling of the transmission capacity of a straight binary system. Let's give an example so that we understand this process in a much clearer way. Consider a binary sequence BK, and this binary sequence consists of uncorrelated binary symbols, zeros and ones, each having a duration of 1 TB. And this sequence is applied to a pulse amplitude modulator, where if you have 0, you give minus A or minus 1, and if you have 1, plus 1. And this is the mapping rule, yes? This is the mapping rule, AK. So what do you have now? You have BK, which is the sequence of bits, and you pass it to an amplitude modulator, let's say, and the result here, AK, is a sequence of minus ones and plus ones. The dual binary encoder converts the two levels binary sequence, which is AK, to 3-level output, namely -2, 0, +2. So from +1, -1, you get -2, 0, and +2. How do you get that? By using this equation. This transformation can be achieved by using this formula. This formula says that the new symbol in the dual binary signaling sequence is CK, which is equal to AK, the current pulse amplitude symbol, plus the previous adjacent symbol. They produce this CK, which is implemented as shown in the next slide. This is the structure of dual binary encoder. You have the input 2-level sequence, AK. What's AK here? 0, 1, 0, zeros and ones, sequence of zeros and ones. BK zeros and ones. AK becomes +1, -1, because it's after pulse amplitude modulation. And you have what? You have here the formula that I just showed you, which is CK equal to AK plus AK minus 1, where K is the index. This is basically the delay here used to produce AK minus 1, and AK is the current value, goes direct without any delay. You sum them, and then you pass them to ideal channel Nyquist filter, and then you sample at time equal T equal K, TB, and then you get your output sequence, which is called CK, which is the dual binary signaling, correlative level coding. Now, this transformation changes the input two-level sequence of uncorrelated binary sequence into a sequence of correlated three-level pulses. So the input basically here, if you AK has only two possibilities, two levels, plus or minus, where the output, and it's uncorrelated. Uncorrelated means it's totally independent. The output now is composed of three values, 0, -2, +2, and these are correlated. Why? Because each value is dependent on the current and the previous value of the original sequence. This correlation between adjacent pulses may be viewed as introducing ISI in the transmitted signal in an artificial manner. So that's why we call it artificial intersymbol interference. Why do we call it, why do we see intersymbol interference here? The reason for that, because this is my pulse, original pulse. When there is another pulse added on top of the original pulse, this means that this pulse will create interference. Isn't that what we call interference? Interference can be partial, can be full, but at the end of the day, it's interference. And since we are dealing with pulses and symbols, that's why we call it intersymbol interference. The symbols are entering to each other's region. And here, it's full overlap interference. They are on top of each other. Now let's understand the mathematical model of this duo-binary signaling. The frequency response of the duo-binary encoding can be derived as follows. The frequency response is how do we define this system in the frequency domain. What do you have? You have here direct path and you have delayed path. The delay, if you have a delay in time domain, when you go to the Fourier transform to the frequency domain, how do you see the delay? Do you know how do you see the delay? As phase shift. Yes, here it is. Because of this delay, you have this e to minus j2 pi ftb. This is due to the delay element, tb here. Here we have delay tb. This is in time domain. I am now going to frequency domain because it's easier to understand things. I want to see them in time and the frequency. And then you have this one, constant. Why? Because you don't have any delay. It's direct constant. And this constant is usually pulses here, we use either raised cosine or sinc. If it is sinc, then it becomes rect in the frequency domain. And well, we have this, the filter or the block that determines the shape of your pulse is this, in H. Nyquist. This is what I mean, it can be rect, raised cosine or sinc. So here we get H. Nyquist multiplied by the response of this system, H. Nyquist multiplied by 1 plus e to minus j2 pi ftb. So here, if you take, here we have 2 pi ftb. If you take just e to minus j by ftb as a common factor outside here, I'm taking it here outside, then I will have e to j by ftb left in the first term, because when you multiply this with this, what do you get? You get e to j0. E to j0 is e to 0, which is equal to 1, which is this. And this, I get what? If you take e to minus j2 by ftb out, you leave here another e to minus j2, e to minus j by ftb. So, as a conclusion, now when you see this form, what do you remember? You remember the cosine. Because cosine, let's say cosine, I want to write cosine x in terms of exponential. What cosine x equals? It's equal to e to plus jx plus e to minus jx over 2. What did we call this? Euler identity. And since we don't have 2 here, then we put 2 cosine. Do you understand from where this came? Now you are familiar. Now this is the final impulse response, the simplified final. Now suppose H Nyquist is rect, which is given by this equation. It's 1 when frequency is bounded between -1 over 2b and 1 over 2b and 0 otherwise. Then the previous frequency response can be simplified as follows. Now H Nyquist, substitute this, just put 1, then you have 2 cosine 2 by ftb multiplied by e to minus j2 by ftb, bounded within by this duration, and you will have 0 otherwise outside of this band. Now this is mathematically, yes, this is the math in the frequency domain. If I tell you find the math in the time domain, then the name of this becomes not frequency response, impulse response, time response. How do you find it? You just take the inverse Fourier transform of this. However, now we understand how to find it mathematically. But what about visually, graphically? Can you draw the amplitude of the frequency response of this signaling in the frequency domain? Yes, you just take the amplitude of this. When you take the amplitude, you just have, this is phase actually, e to j, you just have 2 cosine 2 pi. And when f is equal to 0, cosine 0 is equal to 1, then you have the maximum value at 0, which is equal to 2. Then you draw this, and you find when it is equal to 0, at which point, and you find that it's 1 over 2 TB, and here minus 1 over 2 TB, and then you get this. This is the shape of your impulse, the amplitude of the frequency response of your system. The phase is linear line like this. It's coming from this. Clear? This is math. This is by math. This is by graphical drawing, and this is by block diagram. All of them talking about same thing but different way of representing things to get full understanding of what's happening and what's going. Yes? For example, to explain to you the importance of this math equations and the graphical representation and the block diagram, for example, suppose a patient goes to a doctor. The doctor cannot, from seeing the patient, by just seeing the patient, he cannot give him any treatment. He cannot know what's going on with his body, yes? But if he starts looking at his blood and his temperature and taking ultrasonic images or X-ray images or MRI images, then he gets information from different views, different resources. After that, he gets to understand the situation of the patient. Once he understands, then he can innovate, come up with solution to his problem. The same here. We have concept, we explain it briefly, and then we start understanding its math, the math behind it, the block diagram that generates it, the shape of the signal in time and the frequency, so that we get full understanding of the system and understand how it works and what parameters affect this. Once you understand this, then you can build on top of that, come up with a new solution, give a new treatment, and become innovative like the doctor. Decide things precisely, perfectly. So that's why we call engineers are the doctors of machines. The doctors of, objects. They know what affects them, how they get influenced, how to optimize things, how to improve the performance. You can only do that if you understand the system very well. from all the perspectives, from all the windows. Having said this, we move also to the time domain. I told you to go to the time domain. What do you need to do? You just get this equation and take the inverse Fourier transform. To get the inverse Fourier transform, this is cosine, very easy to find it, and this is e to minus. So you get sinc, something like sinc with shift. Sine by t, tb over pi. If you find it mathematically at home, just practice it. You can find this. And when you draw this in the time domain using MATLAB, you get this pulse. So this is the shape of the pulse in due binary signaling in the time domain. What's the shape of this pulse in the frequency domain? It's this. And this is its phase. So clearly, there is something that you can say about this now. What's that thing? The response of a pulse is spread over more than one signaling interval. As you can see previously, when we studied intersymbol interference and Nyquist symbol pulses, we said that the pulse has around TB duration. But now, it has more than one TB duration. It has almost how many TB duration? 3. So this is the first observation. Can you make this observation without drawing the signal in the time domain? You cannot. Or you must be very good mathematician to know from the equation. But from graphics, much easier. So here, the response is partial in any signaling interval. So here, when you take what does this mean? If you look at the window from 0 to TB, do you get the full pulse? Do you see the whole pulse? No. Just partial of the pulse. Partial portion of the pulse you can see. You need to get 3 TB to see even more to see the whole pulse, how it acts, how it behaves. So now, in order to detect or recover the bits now we talked about the transmitter. Now we need to talk about the receiver. And I told you, whatever you do at the transmitter, at the receiver is the opposite. To detect or recover the bits into its original format, we can reverse the operation made in the modulator according to the following equation. CK was, in the transmitter, at the transmitter, CK was equal to AK plus AK minus 1. Now, you are interested in knowing AK, assuming you know this, because you started from a reference symbol. Then it's the value you receive minus the reference, you get the current, 1, which is this. Basically, you receive your modulated sequence, CK, due binary signal vector, and then you take the previous symbol you already received, you subtract it from CK, and you get the current transmitted bit or symbol. We call this decision feedback detector. Now let's give you an example to make you understand this very well. This is the example. Now apply your knowledge here. This is what, at the end of the day, this is what I want to do and this is what I care about. Let's say you have the binary sequence BK, which is equal to 00101110. And the question says, find the coded sequence CK using due binary signaling and the decoded sequence A hat K, assuming the first bit is the reference bit. The reference bit is 0 here, I'm assuming. So what do? You just write here BK is this sequence, the one I gave to you. Then you say I modulated using pulse amplitude modulator AK because it gives you the pulses. If 0 comes, then it's -1. If 1 comes, it's +1. Then you can now find CK. CK is equal to AK plus AK minus 1. AK is this. AK minus 1 is this. So -1 plus -1, the result -2. Now the next one. plus 1 plus minus 1, 0. Minus 1 plus 1, 0. Plus 1 plus minus 1, 0. Plus 1 plus 1, 2. Minus 1 plus 1, 0. So now you get what? The due binary signal. This is the due binary signal. Now you transmit it over the channel and you receive it at the receiver. You need to know what? AK first. So AK hat, you can find it by taking a CK value and subtract it from a reference symbol, minus 1. Why it's minus 1? Because it was minus 1 here at the transmitter. So minus 2 minus minus 1 means minus 2 plus 1, which is equal to minus 1. And then these are the pulses. You demap them to their bit value. If minus 1 comes, this means that you transmitted 0. If plus 1 comes, means you transmitted 1. We used only this equation at the transmitter, the due binary coding equation at the transmitter, and this is the due binary detection equation at the receiver with a reference symbol. So this is basically how you perform the modulation and detection of due binary signaling using these two equations. Now, what are the disadvantages of this scheme? The due binary signaling code suffers from two shortcomings. First, it has error propagation problem. For example, if a given bit received an error, then the error tends to propagate in the succeeding bits. Let's say you received this an error. Yes, there was an error here. Then, since your equation takes this and the previous one, it keeps its effect on all the upcoming detected bits. Error propagation, bad problem. We don't like it. We don't want it to happen. So, first problem, error propagation. The second problem, it cannot be transmitted over a wireless channel. Why? Anybody can know why? Because when we drew the frequency response, the amplitude frequency response, we noticed that at frequency equal to 0, we have maximum amplitude 2. We all know that DC frequency equals 0, this means DC, not AC. There is no oscillation. If there is no oscillation, you cannot send this like over an AC channel. This is bad, so it limits the application of your scheme. So these are the two shortcomings of this scheme. And in the next lecture, we will understand how we can handle these two shortcomings and fully and deeply explain the precoded due binary signaling coding scheme and how to handle the error, the AC thing by introducing a new signaling process. Thank you very much for your attention, and we continue in next lecture, inshallah.